So it's finally starting to feel like fall outside. Nice and cool in the morning. We're getting towards the kind of the latter part of the semester. It's a challenging time for many students as projects come due and all of those types of things that you have to deal with. I encourage you all to hang in there, though. The end is coming soon, and we'll be away from winter break before you know it. So today I put in several things that I wanted to briefly talk with you about that appeared in some recent issues of Chemical and Engineering News, things that I think you all should be aware of for a variety of reasons. We'll talk about those. I also put in this morning this so-called DCUR RAC card for you to review later. It's on the DePoe Center for Undergraduate Research. I'm going to give you, I tried to invite Dr. Sabina Heinhorst, the Dean of the Honors College, to come and talk to you this morning about the DePoe Center and about undergraduate research. She just wasn't able to make it, so I'm going to do my best. I used to be on the steering committee for that, so I think I can handle most of it. So we're going to have a little bit of an undergraduate research talk today. And then I'm going to move into some of my research and give you an opportunity to see your first faculty member presentation. I'll post some presentations in upcoming Canvas shells to where you can see what folks are working on throughout the discipline. So let's go ahead and just get started. The first thing that I put in was from a series of case studies that were in Chemical and Engineering News on new technologies that were coming forward that they thought were going to be some game changers. One of these is on helium recovery, using membranes to open up new sources of helium. Why is helium important to us from a strategic national perspective? Anybody know? We do have a lot of natural gas, which is where typically those wells is where you will get helium. But we do not control the world's largest percentage, I think, of helium, but we do have a fair amount. What else? Why is helium important to us? When you think of helium, what do you think of? Pardon? Balloons. Is balloons strategically important for us? No. But it is probably where you come into contact with helium the most, right? Valentine's Day, you buy somebody some balloons. They're filled with helium. Birthday balloons, right? Typically filled with helium. What else? Blimps are filled with helium, right? Probably not much in terms of a strategic thing for us. But where else is helium used? Why is helium important? Why should the government control helium? You might have remembered a few years ago we had a helium shortage. You couldn't buy helium balloons. They cut off helium supplies for balloon, or balloon grade helium as they call it, because it's important to divert helium to other uses. Can anybody think of any uses? Really, really, really cold. That's exactly right. Helium in its liquid form is the coldest substance we know of, right? Where might really, really cold things come into use? For those of you who want to go to medical school, where will you be using helium? Anybody ever heard of an MRI? Magnetic resonance imaging? Those systems use superconducting magnets. Those superconducting magnets are only superconducting if they are really, really cold. Okay? And so I would argue that having a helium supply for medical use is certainly much more important than having our helium supply for balloons. Helium is a real problem for us. Because it is so light, it doesn't stay in the atmosphere. It can actually, once it's released, it can actually escape the Earth's gravitational pull and end up in interstellar space. So you can't just recover it from air, right? If we want oxygen, we can get that from the air. We can liquefy it. We can liquefy nitrogen, no problem. You can't do that with helium from the air, okay? you have to get it from wells and you have to store it. Okay, and you have to separate it from other gases like natural gas. And so that's what this was about. How do you build a membrane that allows you to separate helium from other things? And it turns out that you all have experienced this membrane effect with helium. Think about it when you got a helium balloon and it would float, right? And it would get loose and it would be on top of the ceiling in your house or whatever. What happened the next day when you came and saw it? It would have dropped. Why is that? The helium can escape because helium is so small it can actually escape through the pores of a balloon. And think of that balloon as a membrane, right? So the helium can escape out. Well, it's the same kind of principle here, except you really want a membrane that's very, very selective for helium, right? Every other gas will stay within inside the membrane. The helium can come out, and then you can collect it, purify it, and use it. Helium storage is a real problem, right? And so having membranes that can separate it from lower producing wells is very, very important because we only have so many wells that we can get the helium from. So helium is very, very important for keeping things cold. It's in superconducting magnets. Like I said, if you went up on the 4th floor here into the chemistry floor, we actually have what's called an NMR. You'll learn about that in organic chemistry. It is a superconducting magnet that is cooled with liquid helium. It has to be filled with liquid helium twice a year. And then when we had those helium shortages, we were kind of panicking about whether or not we were going to get enough helium to keep that. Because once it raises to a certain temperature, a superconducting magnet is no longer superconducting and it dies. And since it's a $500,000 piece of equipment, you don't want that to happen. Right? So you have to constantly feed it helium. Yeah?
How much are the liquid helium refills running?
It's been a long time since I have looked at that. My wife would know better than I do because she's the one that actually does it. And we work with Polymer because they have a number of NMRs, so we try to order our helium in bulk. But I think it's at least $1,500 a fill. I mean, it's very expensive. In fact, some universities have so many of these NMRs that they actually have these reclamation systems to reclaim the helium so that they can not waste it. Because helium has gotten so expensive that you can actually now think about cost-effectively reclaiming helium. So anyway, that's why this one, it's an important issue. Can you imagine going to the hospital and needing an MRI and them telling you, sorry, we're out of helium? That's a real issue in parts of the world. And it's going to be an issue here if we can't figure out better ways to store our reserves of helium. In fact, the federal government has a helium reserve. And a lot of people in the past had criticized it because a lot of people think of helium as balloons. Why is the government storing helium for balloons? They're not. They don't care anything about your party balloon. What they care about are your medical things, the research that we need to do. This piece I thought was interesting. Cassandra Quave, plant hunter. I found that kind of humorous. Botanist, chemist in a way. What was important about this piece?
She wanted to research plants because she thought about the fact that there's so many that we've never researched.
That's right. There's plants all over the place that we've rarely spent research on, especially ones that we consider weeds. We try to kill them, right? But what do we know about plants?
They can be used for medicine.
They can. I mean, we know that there are traditional medicines, right? Or native medicines, whatever you want to say. Medicinal plants. You may know that on campus, over by the Baptist Student Union, we actually have a medicine wheel, which is all of those native plants that are believed to have medicinal properties, so people can go there and pick what they want and whatever they want, make their tea, their rubs, whatever they need to make. So there is a lot of medicinal compounds that we actually find quite a bit in plants. Okay? Scientists have to get inspiration from somewhere. Nature is very good at making molecules, and so we quite frequently look to nature to find molecules that might be anti-cancer, other types of drugs. We always look for those types of things. And so you need people that can go out in the field, identify various plants or animals, whatever the case may be that we're looking at, bring them back to the lab, and then actually analyze whether or not those plants have medicinal properties. Is that enough? Are we done once we've identified a plant with a medicinal property? No. You then have to identify the compound that is responsible for those medicinal properties, because a plant will have thousands of molecules, if not more, right, that you can detect, and you've got to figure out which one is the medicinal compound. Why is that important? Why can't we just grind up the plant, send it to folks and say, here's your medicine? Sometimes we do. You might buy herbs, right, herbal supplements, but why in general do we not do that?
That's not the part that's helpful.
Okay, there's also in many plants things that are toxic. So there are many plants that may have medicinal properties, but also have toxic properties that you gotta keep in mind. What else?
We might not be able to grow that plant in bulk and harvesting it from the wild.
That's right. So if you think of the molecule Taxol, for example, it comes from the yew tree. They found Taxol in the bark of this tree. If you strip a tree of bark, what happens to it? It dies, right? You can't just go and strip a tree completely of its bark and then it regenerate, especially this particular tree. And they found a compound that they called Taxol, very potent for breast cancer treatment, very, very potent. It's like the #1 drug to treat breast cancer. To treat just a handful of people, we would have had to have decimated a forest of those trees. They're fairly rare, okay? They don't just grow in our backyard. They're not, these popcorn trees that keep popping up everywhere, right? The things that seem to pop up everywhere seem to have no medicinal value, unfortunately. And so you had to have a chemist, once that compound was identified, to actually figure out what its structure was, how everything was oriented in space, how everything was connected. You then had to have a chemist figure out, how can we make that from something we have more abundantly? What do we have in abundance that is organic? Oil, right? So organic chemists come in and they say, how do we take petroleum, the things that we get from petroleum, and convert that into an identical molecule that the yew tree makes that can fight breast cancer, okay? So that's very, very important. And so there's a lot of people that get a lot of inspiration and love going out and doing these kinds of hunts, if you will, to find new plants and then to come back into the lab to see whether or not they have some type of medicinal properties. It may take people years to finally figure something out in this way. It's not just like going out, picking up some plants, coming back to the lab, and having the next cure for cancer. It just doesn't work that way, okay? People don't just look at plants, but they also look at marine natural products, as we call them. One of the individuals who was on my PhD committee at the University of Oklahoma was one of the world's most renowned marine natural products chemists. Every year, he and his graduate students went to Hawaii for about 3 weeks, and they did all these dives, and they collected sponges and other types of marine animals, and they preserved them, brought them back to the lab and processed them, and spent the rest of the year trying to figure out if any of those animals actually had medicinal properties. A very long and laborious process. And to my knowledge, I don't think he ever found a molecule that ended up being commercialized as a drug, okay? Most of the time you don't find those types of things. But the world has an entire huge library of molecules that we can, so quote unquote, screen against. And so that's one of the reasons why I picked this one as well. If you're interested in nature and getting out, this might be something you might want to think about, is to get into natural products chemistry. There's been a resurgence recently in big pharma. There's going to be a lot more jobs in the next 10 years to try to find molecules that can treat this new thing that we got going around called COVID. You all know about messenger RNA and that those vaccines. Vaccines prevent you from getting it, they do not help treat you if you have it, right? So we really need small molecules that should you contract COVID, we could actually give you to help mitigate the piece or the side effects. The last piece from Chemical and Engineering News, if it'll pop up here, was an article, come on Moderna. Moderna announces plans to make vaccines in Africa. Why is this relevant?
They have a short shelf life.
They do have, they do have. These things had to be shipped cold. Yep.
Like 4% of Africa is vaccinated.
Okay, a very small percentage of Africa is vaccinated. What else? So to get back to what Megan was saying, right? If you have something that you got to ship cold, the longer the distance, you're going to need a lot of dry ice. You might need liquid nitrogen. You need cryogens. You need a way to keep it cold. So you want to manufacture it as close as possible to the area of greatest need. And there's a great need, as you mentioned, in Africa to get more and more people vaccinated. I also view this as a social justice kind of thing for the industry. Industries aren't, even though some people have this vision that industries are out there to just make money, yes, that is the driving force of business. There's no question about that. But these are people that actually do look at social issues as well, and they try to do socially conscious things within their company to help benefit the world. If you think about it, we can have the United States completely vaccinated within the next few months, practically fully vaccinated in the next few months. But if the world isn't vaccinated, we are still going to be faced with variants. You can't have hot pockets where the virus is allowed to replicate and mutate and then propagate, right? So it really is a global pandemic, right? It really is a global health issue. It's not just, the virus doesn't recognize the borders of the United States. It does not recognize the borders of Europe, right? It will not stop at those borders. And it will get through. You cannot stop it unless you take a more global picture with it. And so I really do think that it's a great thing that Moderna is planning on investing a significant amount of money in Africa to actually have these manufacturing facilities there so that they can quite readily manufacture and get it into the arms of people who need it and try to help bring down the spread of COVID-19. So this is a more business-oriented piece, but I thought it was a very nice piece showing how companies are thinking about broader pictures other than just the bottom line. Okay. All right. You all can look at that Decur rat card on your own. Now what I want to do is spend a little bit of time talking with you about the DuPont Center for Undergraduate Research, not undergraduate search, I'm sorry. Let me give you a little bit of history on this. It started out as just CUR, the Center for Undergraduate Research. That was formed probably 10 years ago now, if I was to guess, and if my memory serves. Maybe a little longer than that, when Dr. Dennis Wiesenberg came to the university as the vice president for research. He eventually became a provost, but when he came here, he came as the vice president for research. And one of the things that he noted was that a lot of research groups here on campus, like in chemistry, like in biology, like in polymer science, worked an awful lot with undergraduate researchers on projects. And he said, you know what, it's one of the things that we seem to do very well. Let's put together a center and let's support it. So that's what the center is designed to do. The center is a resource for you all, not for people like me. for people like you, okay? For students. It is a resource that you all can use to get your research funded, okay? So he started that. Just to let you know, to get a center started within a university, you actually have to go to the state to get that approved. He did. USM was the first in the state to have a center for undergraduate research. We take it very, very seriously. It's one of our hallmarks. It is one of the reasons why so many of our students get the Barry Goldwater Scholarship, get NSF fellowships to go on and do graduate studies, etc. Okay? So the Center for Undergraduate Research was formed. They formed a steering committee that helped distribute about $50,000 or $60,000 a year to undergraduate students to do the research. I was on that steering committee for a number of years. It was very exciting to see the applications come in and see what the students were working on. Then came along a benefactor, Mr. Donald Drapeau, who said, you know what, I came here as an undergraduate student. I believe he was a history major. I think he had an undergraduate research or project experience that he really liked. He actually ultimately went off to the Mercantile Exchange and became a multimillionaire. And so he decided to give us a great gift to support the center. And so the center now bears his name as the Drapeau Center for Undergraduate Research. The center operates a number of programs that are there to benefit you. First and foremost, we have what's called the Eagle Spur Award, which has deadlines of October 15th and March 15th every year. So obviously the October deadline has gone by. But if you're thinking about applying for an Eagle Spur Award, the next one would be due in March 15th. It's a proposal. You submit that, what your research plan is, what you need the money for. And if you get funded, you will receive that money. Well, actually, you don't actually receive the money. Your mentor receives the money to spend on your behalf. Okay? And so you can buy research supplies with this. You can pay for travel if you need to go and do research somewhere. You can also pay yourself out of it, right? Your time is a valuable resource, right? And so if you're having to work to make ends meet, you might be thinking, well, I really can't go do research because I got to go and work at wherever. But you can, quote unquote, buy yourself out from your other job and pay yourself off that grant so that you can actually do the work. Those are about $1,000. I think maybe a little bit more with some. It's 1,000 max. Yeah, it still is about 1,000 max, which doesn't pay yourself a whole lot if you're paying yourself, but can certainly go to travel, etc. Just to give you an idea, research for this is not just considered scientific research. Social sciences also apply, business applies, and we also consider research to be creative activity. So your friends who are in the humanities and the arts have also applied and gotten awards to put together a variety of things that they consider research within their area. So it's a very broad organization. They also have a Drapeau Summer Research Award that they give, which will pay your stipend for the summer, which is more than $1,000. That's due by March 15th. So if you're thinking about, you know what, maybe I'd like to get my feet wet in a really good summer research experience, but I'm not ready to go off to California or North Dakota or wherever to do a REU type program that we've talked about before, you could do a summer research experience here. Get that funded through the Center for Undergraduate Research, and have your experience. The application portal is what they call InfoReady. You'll see there's a place, a link, and I'll put this in the Canvas this afternoon, so you'll be able to go. But if you go to undergraduate-research, you'll be able to find all of this information. You'll be able to find the link to InfoReady. You'll be able to go in and perform an application or put together an application. There's also this new thing called Funds for Unanticipated Opportunities. I'm not exactly sure what that is, but I think it's similar to what NSF has, which is called RAPID. So there are things that happen very, very quickly that you don't have time to go through the normal process to get funded, right? So for example, at the NSF, just to let you know, let's suppose a volcano's getting ready to erupt. We just learned that yesterday. It's going to cost $1 million to get all the stuff that we need up to the volcano to figure out and measure all the things that we need to do. Well, you don't have 6 months to a year for a proposal to come through. So you have what are called these rapid proposals to take advantage of these things that happen very, very quickly. And I think that's what this is as well. Okay, so, COVID's a perfect example, right? I mean, COVID just happened. And if you wanted to study the impacts of COVID somehow, well, you're going to have a way to do that. And apparently they have a rolling application deadline, which of course, obviously, since it's unanticipated, you can't say it has to be due by March 15th, right? So that's how that works. The center is funded, like I mentioned, by Mr. Donald Drapeau, but also by the Office of the Vice President for Research. So they fund about 20 to 25 projects a year with the regular Eagle Spur, and they get about 40-ish applications, I think. So you're looking at about a 50% success rate. You all might think that's not very good. In my world, that's great because normal funding opportunities, typically you're looking at 10 to 15% funding rates. So you all have really good chances of getting things funded. At least when I was on the center's steering committee, students that didn't get it the first round quite frequently got it the second round. So that's why it's important to get started on your research early. You can put in, and if, it didn't get funded this time, you can make some tweaks, resubmit the next go round in the next funding cycle, and make that happen. Yeah.
I just put in my Eagle Spur proposal a couple weeks ago.
Oh, good.
I wanted to comment, because I know when I was a freshman, I was like, oh my gosh, I gotta come up with a research question all by myself. You don't have to come up with something entirely by yourself. Most of the time when you're doing undergrad research, you're looking at your advisor's research interests and picking out a specific point within their current research to delve into further. And the proposal itself, I think I wrote about 2,000 words for it, so it's really not that bad. It's like 2 pages. But yeah, so just if you're
That's excellent, and congratulations on the submission. These submissions, if you get them funded, not only do you get the money, you also get the opportunity to put that on your CV as a competition that you quote unquote won, right? Those types of things will set you apart in your applications for medical school, graduate school, whatever the case may be for you. The center also runs this thing called the Student Opportunity Center. I'm not particularly familiar with this, but you can find that at studentopportunitycenter.com. You can create an account. I think it is free for you, but you'll be able to go through and find different types of undergraduate opportunities for research and creative activities. So you can find things on internships, conferences, funding, scholarships, and also access to journals for publication of your work. So there's a lot of ways. Southern Miss faculty do add opportunities to this. It is one way for you to go out and figure out who's doing what. However, I personally believe, while this is great, your best chance of figuring out what people do is to talk to people on campus. Go to professors who might have things that interest you. Look at their web profiles. Go to the web for those faculty in your area that you might be interested in. If you're interested in biochemistry, go look and see what Dr. Rangachari is doing, or what Dr. Huang is doing, or what Dr. Kessel is doing. Things of that nature might interest you, right? And we'll learn more about their work later on this semester. But Dr. Rangachari, for example, does things with Alzheimer's. So if you're interested in that kind of disease state and want to study it, he might be a choice for you. Dr. Huang does things with RNA. So if you're thinking, hey, I like this messenger RNA stuff that we've been hearing an awful lot about, Dr. Huang's group might be a perfect fit for you. And Dr. Kessel actually does research on HIV. So if you're interested in a more medical, relevant type of project, right, things that obviously we can find drugs for right now, you might be interested in his research. On the chemistry side, If you're interested in actually figuring out what is in stuff, that's more analytical chemistry. Dr. Meow does that. If you're interested in how do I sense things that might be in the air or the water, or how do I sense toxins or potential explosives, that's the kind of work that Dr. Wallace does. If you're interested in how do we make molecules, that would be more like what I do or Dr. Donahue does or Dr. Pigza. Dr. Donahue and Dr. Pigza do more medicinal chemistry than I do. I do a little bit, but they do an awful lot. And they actually have a collaboration with Dr. Kessel on the HIV project. So you could actually have most of both worlds if you were to work with Dr. Pigza or Dr. Donahue. And then we also have a physical chemist who is interested in polymers and fibers for better solar cells. So if you're interested in energy and energy conversion, renewable kinds of things, you might be wanting to reach out to Dr. Guo. His work has been funded for a long time trying to identify new ways to make these devices more efficiently. And I'm using a very high level discussion here. Okay, but you can also find other things on the Student Opportunity Center or the SOC. Okay. The other thing that the center does is they host the Undergraduate Symposium, or what they call UGS, and it's on research and creative activity. This is an annual conference that actually got started back in the old College of Arts and Letters back in the day. It has been folded into the center, and it is an excellent opportunity to go. Even if you don't present, you really should take a time and go and hear what some of your colleagues are doing across campus. This is actually Mr. DePoe typically shows up. I don't think he did last year because it was all online because of COVID. I hope this year they're going to do it face to face. But usually Mr. DePoe shows up, meets with all the winners, actually hands out the award checks. I forget what the cash prize total is, but I wouldn't be surprised if it's not $25,000 or $30,000 to that one day that's handed out. I mean, it's a lot of money. So there's a lot of big cash prizes that are handed out as you compete during your presentations. So they do oral presentations where you're actually up talking like I'm talking to you right now about something. They actually have poster sessions where you stand by your poster and people come by and talk with you about your work. If that's more comfortable for you, they do that. And then they always have a keynote speaker that usually comes and talks. They do some type of art showcase where the artists are out either showing their works or actually doing something like a dance or a performance. And then there's a big award ceremony at the end. So it's really a day filled with a lot of energy and a lot of enthusiasm, I guess I would say. So I would encourage you, if you're thinking about doing undergraduate research, to go. Right now it's scheduled for April the 23rd, which is, these are always on a Saturday. I would go ahead and make note of it because you'll really get an idea of whether or not research is something that you might want to do by seeing what your colleagues have done. So I encourage you to attend the symposium, and it is one of the requirements if you get an Eagle Spur Award or any of their awards, you have to present your findings at the symposium. So this is one of the ways in which you would disseminate your results, which is part of the scientific method, right? You're actually publicly presenting your information to others so that they can learn from what you have done. Is there any questions about the symposium or the center? Okay.
It's here?
Huh?
It's here?
It is here, yep. So typically the symposium is held over in Siena Hall, out in that area, the common area on the first floor of Siena. All day long they've got snacks and they've got t-shirts. I think if you go to the symposium you get a t-shirt and you get a bag of goodies and it's a really friendly environment, and then you can go off into your different breakout rooms for the various things that are occurring.
Is this different from requesting to be on a research team with a researcher and like having it as a class sort of thing? Is this a different thing?
This is different. They can be the same, but this is different. So What you're referring to is how you'd get involved in the research enterprise. So going and asking a faculty member about what they do, whether or not it's a good fit for you, you getting into their lab and starting work. None of that has to be funded by the Center for Undergraduate Research. In fact, most of it isn't, right? Most people in chemistry have money and can already fund your work for you. So you might not need to write an Eagle Spur award, but you can. You can actually be in a class for research, getting credit for it, and do stuff with the Center for Undergraduate Research. So it can be together, but it doesn't have to be. You can actually do something with the Center for Undergraduate Research totally unrelated to what you're doing in your major. You could find somebody who, if you had an interesting question you wanted to answer, you could write a proposal, find a faculty mentor who could help you with that, and that could not even be tied to chemistry if you wanted to. It doesn't have to be tied to your major to go through the Center for Undergraduate Research. Did I answer your question? Okay, good. All right, so I highly encourage you all to visit the website, get familiar with the Eagle Spur stuff. It is exciting stuff. All right, so today I'm going to present to you some on my work. I don't take many undergraduates anymore, unfortunately. I take maybe 2 or 3 a year to work in my lab. I still have one graduate student, which helps out an awful lot. If you were to decide to try to work in my laboratory, there is one caveat. Given my administrative role at the university, I'm really not available Monday through Friday. So all of my research students know that they have to come in on Saturday. Just telling you that up front. So typically, my research students will come in at 9 a.m. on Saturday. I spend 3 hours with them, helping them set things up or talking with them about their process, helping them solve problems, whatever the case may be. We typically then go and do a group lunch, and then they're usually done by noon. And then they come in and work with my graduate student during the rest of the week. So to get the one-on-one with me, that's typically done during on Saturdays. So I know that's not convenient for a lot of people, and I understand that, but that's just the only way it works for me. So in my lab, we have actually worked on developing methods that actually have some potential uses in pharma and biotech. So I consider myself a bioorganic chemist in a lot of ways. What does that mean? It means I'm a chemist, I'm not a biologist, but I work on areas using my skill set that might have applications in biology. Okay? So those are the types of things that we do. And I do have collaborations across the globe. Most of my collaborations now are in the United States. We've got collaborators in Vermont right now that we're working with. I've got a collaborator in Minnesota. I've got a collaborator in Virginia. And I have collaborators in Germany. And those are the ones that are shown here. I've got a collaborator, Dr. Uwe Bornscheuer at the University of Greifswald. It's kind of in the old eastern part of Germany. We went there about 10 years ago, visited his facilities, attended a conference at Enzymical. That's the company that he started. And it was really kind of an interesting collaboration for a lot of years. It's kind of dwindled down a little bit because we kind of run our course, but we still do collaborate from time to time. And the nice thing about the collaboration, from my point of view, is that they provide me with their library of enzymes that we can use in our chemistry. So we've already talked a little bit about some of this, but in my lab, we really do deal with this thing called chirality, and we've talked about that in class, right? It's handedness, right? When we built the molecules and we went around, we noticed that some were right-handed, some were left-handed. And while you might think hands are the same, they're actually not superimposable on one another. So they are different. A right hand will fit in a right-handed glove, but it won't fit in a left-handed glove. It's a very important thing for biology, and I'm going to show you why. Okay? So for example, if you look at thalidomide, many of you may be familiar with this. These are mirror images of thalidomide. If you actually took this and laid one over on the other, you would find they can't be superimposed. This atom on both of them is what we call the stereogenic center. It's where the chirality is. Okay, so one of them is right-handed, one of them is left-handed. These enantiomers were actually given to pregnant women many decades ago because one of the problems with expecting is that you might experience severe nausea. And so scientists were searching for ways to help treat that. And it turns out that thalidomide is an excellent anti-nausea drug. But one enantiomer is the anti-nausea drug. The other enantiomer is not harmless. It's a teratogen, which creates extreme birth defects in children. There was this huge thing that happened, I think it was like in the 60s, early 70s, where a lot of women who were taking this anti-nausea drug were having an unusually high number of births that were severely deformed. And so they had to study this, and it turns out that one enantiomer is the anti-nausea drug, the other one is the teratogen. The unfortunate thing is that you can't just give the anti-nausea drug and be okay, because actually in the body, your body has enzymes and mechanisms that actually convert this enantiomer into that enantiomer. So you can't give people thalidomide for an anti-nausea situation. It's just too hazardous to the unborn fetus. More closely aligned with things that you all might be dealing with on a day-to-day basis. After class, you might have a headache. You might want to take some Aleve, right? Aleve is actually made of what's called naproxen or naproxen sodium. They usually give this to you as the sodium salt. You have to have S-naproxen in that tablet. It can't be a mixture of both enantiomers. S-naproxen is the anti-inflammatory, so it lowers your fever, lowers inflammation, helps with joint pain, and will actually, it's an antipyretic as well, so it will lower fever. That's what S-naproxen does very, very well. If we gave you R-naproxen, we would destroy your liver, okay? And so it's very, very important is how we develop methods to make one over the other. You don't want to make it as a 50-50 mix like we did the other day with that exercise and then figure out some way to separate it because you got to throw half of it away, right? That's wasteful. So chemists have figured out a way to only make S-naproxen. And you make S-naproxen and you get that in your pill. Now, there have been an awful lot of Nobel Prizes given for people being able to develop ways of making things chirally pure, okay? This last Nobel Prize that we talked about on organocatalysis largely was about making things enantio-pure. But other Nobel Prizes have also been given for this because it's so important, okay? It's probably the single most Nobel award-winning broad topic, at least for chemistry, okay? So I just want you all to know, every time you go and buy a bottle of Aleve, a chemist has had to figure out how to make it and analyze it for its purity in a way to ensure that you have the anti-inflammatory agent and not the liver toxin, okay? I got interested in my work from what was published early on in the 2000s. The National Academy of Sciences assembled a committee of very prominent chemists to come up with the challenges that we would be facing chemistry-wise in the 21st century. And these are some of the things that they came up with that we're going to have to really, really work hard at this century. We're already a fifth of the way through the century, right? So, where do we stand on all of these things? Well, they said, you need to be able to design synthetic procedures that can be optimized for specific properties of products. We need to develop methods that can enable the synthesis of all important molecules in reasonable yields using compact synthetic schemes. What does that mean? It means cut down the number of steps. That's really what it means. Some of the drugs that you might be taking, or people that you might know, they may have a 20 or 30 step synthesis. Guess why that drug costs so much? Every step requires somebody to figure it out, optimize it, purify it, isolate it, move it on to the next step. Steps are equal to money, okay? They also said, and this is the important one for me, they wanted more research on incorporating enzymes as catalysts in the synthesis and manufacture of important materials. What do we know about enzymes? Enzymes occur in biology, right? They're prevalent. Quite frequently, they're actually cheap to isolate from the source. And we also know that they are some of the most efficient catalysts because nature has spent millions of years optimizing them through natural selection, right? So instead of starting from scratch, hey, let's use what nature has. Let's be like that plant hunter, and let's find what's out there that can do the chemistry for us. And then, of course, devising good manufacturing processes that are not only efficient but environmentally benign. How can we do more chemistry in water as opposed to, some organic solvent that's toxic? That kind of stuff. So these are the things that I took from that 100-page report that I thought, I have some skills that we can use in this area. So in my lab, we use small molecules. These are called malanates. And don't worry about the word prochiral. You don't really need to spend too much time worrying about that. But what you need to know is that I can give that molecule to an enzyme, and that enzyme will chop off one of these so-called ester groups and replace it with what's called a carboxylic acid. And in doing so, I have now created a chiral molecule. Okay? So this molecule isn't chiral, it's easy to make. This one is chiral, it's harder to make, but the enzyme can do this work for me. Okay, so this is the right-handed version. And the enzyme can give me that right-handed version almost completely pure. We can then take this molecule and I can make things like alpha amino acids, beta amino acids, gamma amino acids. We've done a variety of different things. Why are amino acids important? They build everything. They are what puts your proteins together. It's what your muscles are made of, right? Amino acids are very, very important. Nature typically, depending on who you talk to, uses 20 or 21 natural amino acids. What we are making are called unnatural amino acids, okay? And we can take those amino acids and we can use them in kind of some cool ways in a medicinal setting, okay? So our first job was to figure out this chemistry very well, and we've spent an awful lot of time doing that. That's where the collaboration with Enzymical has come in. But we get our enzyme from pigs. We use what's known as PLE, called pig liver esterase. This enzyme is amazing. It is cheap. You can literally go to a slaughterhouse and get a pig liver and make your own if you wanted to. I would not recommend doing it because it is so cheap, just to buy it already prepared. But it is a very, what we call, promiscuous enzyme. It will react with a lot of things. Okay, it'll do a lot of chemistry. There is one problem with it, however. Can anybody think of what might be a problem if I was going to make a medicine using this process and I'm going to use something that came from a pig? It's not kosher. So there's a lot of people out there who would not be able to utilize the product that I just made because it's not kosher. We actually use something from the ground up pig liver, all right? There is also issues with using things directly from the animal source because you can actually get disease transmission through that and other things, okay? However, we do use pig liver esterase. But Enzymical came along and they actually have a way of expressing that enzyme in E. coli. So you're not actually using the animal source. You're using a more biotechnology source for that enzyme. And that's where we got involved with Enzymical, because not only can they do that, which makes it kosher, interestingly enough, but also they can tweak the enzyme. They can use biotechnology to make it more efficient, more selective, and we have various different types of pig liver esterases that we can use from them. And we've studied all of these things in this type of chemistry and figured out what we need to do. Okay? The importance is things like this. All right? So this is called somatostatin. It is a small peptide, meaning that each one of those circles represents an amino acid linked together. It is a loop structure. The interesting thing about somatostatin is that it will bind to a cell through what's called a somatostatin receptor. And the interesting thing about that is a lot of cancers actually overexpress the somatostatin receptor. Why would that be important? If I'm going to give you an anti-cancer drug, what do I want the drug to work on? I want it to work on the cancer and only the cancer, and I want it to leave the good cells alone, right? Most anti-cancer drugs kill everything. And what you hope is that it kills the bad cells before it kills too many of the good cells. That's why you get sick if you're on cancer therapy, because that treatment is going after everything. And it just so happens that cancer cells quite frequently will die faster than your healthier cells. Okay, for a variety of reasons we don't need to get into. But many cancers actually overexpress these somatostatin receptors on the surface of the cell. So imagine if we take somatostatin and attach the drug to it so that it will bind to the cancer cells more readily than a regular cell, and we can use this then to deliver the drug to the cell that we want to kill. Okay? And it turns out that pancreatic tumors typically overexpress somatostatin receptors, acromegalia, cervical cancers, and endometrial cancers quite frequently overexpress somatostatin receptors. So the idea is, let's take somatostatin, it'll bind to that somatostatin receptor, and it will carry a toxic payload with it to deliver to that cell. But there's a problem. The problem is that small peptides like this are rapidly degraded in the body. If I was to give you an injection, which I would not do, but if I was to give you an injection of somatostatin, in about 2 minutes, half of that somatostatin that I injected you with would be degraded. 2 minutes after that, half of that remaining. So after about 6-7 minutes, pretty much so all of the somatostatin that I injected you with would be degraded. Which means what? It probably wouldn't have made it to where it needs to go, right? It just has what we call a short half-life. And the areas that I have indicated with arrows are places where we know the body attacks it and cuts it, breaks it up. So the idea was, why don't we replace some of these amino acids with some unnatural amino acids that the body can't degrade? That was our thought. And so we actually did this. We collaborated with a fellow at LSU Health Science Center. We made these somatostatin analogs, and unfortunately it turns out when we changed lysine into our unnatural lysine, it no longer bound to the somatostatin receptor because it changed the configuration of the somatostatin so much that it wouldn't recognize the binder. Okay? Now, if you think about cancer deaths in the U.S., now this is a 2006 estimate, so it's pretty old, but a lot going on there, right? So we were interested in being able to alter the size of the loop and change the length of the spacer. We've done all of that kind of studies, but unfortunately you really need lysine there. And so we ran into a bust. So we're doing more things these days with it. The last thing that I'll talk about is using some unnatural amino acids that might have potential as an antimalarial agent. So we actually made the molecule that you see there. It's called glutathione. Glutathione typically has a hydrogen atom here, but in this case we put a carbon. Okay? And so it's unnatural. Glutathione, every one of your cells has a lot of glutathione. Glutathione is used for a variety of purposes in the body, but one of the things that it's used for is to detoxify, and it's also used to keep your redox in balance. So we don't need to get into a lot of details there, but it's called oxidative stress, okay? It's the important thing. And glutathione is typically processed in your body by an enzyme called glutathione reductase to make what's called the free thiol form of glutathione. It's the active form that detoxifies things in your body, helps keep you from undergoing a lot of oxidative stress. It keeps you from going rancid, okay? We are full of fatty acids that can go rancid. This helps you from going rancid. Well, it turns out that our version of glutathione, where we have changed and put those carbons, when it interacts with glutathione reductase, it actually turns off glutathione reductase. It doesn't undergo reduction, okay? And that has potential as an antimalarial, because it turns out that the malarial bug, if you will, is very susceptible to oxidative stress. So if you can increase the level of oxidative stress within that plasmodium, you can actually kill it fairly easily. So we did a bunch of studies where we looked at how our glutathione inhibited glutathione reductase to see whether or not it would be a viable inhibitor with potential antimalarial activity. So for that, I think I'm going to stop today, so you know a little bit about what I do. And we will try to introduce a different faculty member or two each class for the rest of the semester. So just to remind everybody, your second activity is coming due. So if you haven't done that second activity, you need to get that done quickly. And also your second one-on-one meeting with me. I've had several already, but please go ahead and get that scheduled with me so that we can have that second one-on-one before the end of the semester. I forget what due date I gave for you to schedule it, but it's coming up. The 12th? Yeah, so we need to have that scheduled by the 12th. We can go past the 12th for the actual time to meet, but please have those scheduled by the 12th with me. And then, like I said, the semester is coming to an end. And so I wish you all the best of luck, and I will see you all next week.